In this lesson we do some work on mathematical induction, and we're going to concentrate on proofs involving series. Examples. First one, we're going to use mathematical induction to prove that for all positive integers n, this result is true. Now 1 plus 3 plus 5 plus 7 plus, and it keeps on continuing till we get 2n minus 1. We're trying to prove that it equals n squared. So we're going to let Sn be that. Now we need to follow a few formal steps. Okay, step 1 is to prove that the statement is true for n equals 1. So when n equals 1, if we substitute that in, basically we're looking at the left hand side. Look at that last term, really. 2 times 1 minus 1, and that works out to be 1. The right hand side, when n equals 1, is 1 squared, which of course is also 1. So both left hand side and right hand side equal 1, so therefore the statement is true for n equals 1. So there's our statement there. Let's just make some room for ourselves, move it up there. Step 2, we're going to assume that the statement is true for n equals k. That is, assume s of k, which is 1 plus 3 plus 5, etc., 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 all the way equals k squared, where you can simply see we've replaced the n with k. The next step is to try to prove that Sn is true for n equals k plus 1. That is, try to prove s k plus 1. The way we do that, we write down what we've got so far, sk, and sk plus 1, we're after the next term. So we put that next term for k plus 1 into that, and we get 2 times k plus 1 minus 1. And where we have equals to n squared, where n equals k plus 1. So we're hopefully going to prove that it equals k plus 1 squared. Now that looks fairly formidable, but let's break it down. That first part there, that's the left-hand side, and most of the first part there of that left-hand side is what sk is. So I'm just going to replace that with sk. And then if we expand the brackets there and simplify, we get plus 2k plus 1 there. Now sk, well, from our assumption, sk is in fact k squared, so we just simply write it k squared for that. Then we have the plus 2k plus 1, and if we factorize that, hopefully you recognize it's a perfect square. It equals k plus 1 all squared. And k plus 1 all squared is in fact the right-hand side. So we make this statement there. Therefore, Sn is true for n equals k plus 1 if it is true for n equals k. And in step 3 we say, well, since Sn is true for n equals 1, then it is true for n equals 2, and hence for n equals 3, and so on. Hence, Sn is true for all positive integers n. Our next example, we need to use mathematical induction to prove that for all positive integers n, this result is true. So again, let Sn equal that result. First step, we need to prove that it's true for n equals 1. So for n equals 1, the left-hand side, and putting the 1 there, we get 1 cubed, and 1 cubed equals 1. The right-hand side equals, so substituting n equals 1, we come up with that, and calculating that, that also is 1. So we have the left-hand side equals 1, the right-hand side equals 1, therefore the statement is true for n equals 1. Now there's our statement. Again, let's give ourselves a bit more room. The second step, we assume that Sn is true for n equals k. That is, assume sk, which is 1 cubed plus 2 cubed plus 3 cubed, etc. And basically all we've done there is replace the n's with k. Then we try to prove that Sn is true for n equals k plus 1. That is, try to prove sk plus 1. So we write down what we've got up to k, that's up to k, but then we also want k plus 1 the next term. So the k plus 1 for n, we get plus k plus 1 cubed. And this is where you've got to be a little bit careful. It's not hard, but just make sure that wherever you see n, you replace it with k plus 1. So that statement we're trying to prove, let's break it up. Left-hand side firstly. Right, that first part was sk, and then we had that next term plus k plus 1 cubed. Now sk, from our assumption, we can rewrite it as 1/4 k squared times k plus 1 squared. Then we've got plus k plus 1 cubed. Well, before writing just that, I'm just going to break that up a little bit. I'm going to break that up as to add k plus 1 times k plus 1 squared, because if you look at the proofs, we're interested in having these squared terms involved. Now the other thing to look out for, we've got 1/4 there. So what we're going to write there, we're going to write 1/4 times 4. Okay, 1/4 times 4 is simply 1. So we put a 1 there effectively. Now why have we done that? It's because we need to factorize. Look at the two terms. Notice that 1/4 k plus 1 squared is common to both terms. So we pull that out as a common factor. Then we put the brackets. Then effectively we write whatever's left. So the first one would have k squared left. And in the second one would have plus 4 times k plus 1. So we write that down firstly. And expand the brackets there would have k squared plus 4k plus 4. So again, write that down. And the k squared plus 4k plus 4, do you recognize what that is? Okay, well that is a perfect square again. It is k plus 2 all squared. So what we've got now is in fact what we were trying to prove. So we can say that that equals the right-hand side. As a result, therefore, Sn is true for n equals k plus 1 if it is true for n equals k. Right, now step 3. Since Sn is true for n equals 1, then it is true for n equals 2, and hence for n equals 3, and so on. Hence, Sn is true for all positive integers n. Excellent. Well, that concludes the lesson. Good luck with your questions.